Welcome to the part 4. In this part, we'll study logarithms. As previously stated, logarithms is a modern day mathematics. Logarithms are also the extension of exponents. As I have already stated to you, when exponents and powers became complicated forms, we introduced logarithms to simplify them. Stay tuned in this part, and in this part we'll study logarithms, their basic definition and their major operations. Hi, in this part we will look at logarithm. Now, what is basically logarithm? Logarithms are forms you have read. Log, okay, it is represented something like this. Okay, now why this equation comes? It basically comes, it is derived from the form of exponents. Now when exponents, they become tough to calculate, they are converted in the form of log so that it can be easily evaluated. Now how do we do it? How do we convert it from exponents so that we get easy evaluations through logarithm? We'll have a look at that. Logarithm basically is defined for variables for which x is greater than 0, b is greater than 0, or my b can be equal to 1. Okay, so these are the basic criteria that you need to have. So if I write something like this, y is equals to log b of x, it is actually equivalent to some number x which is equal to b to the power y. Now when this b to the power y becomes difficult to solve, we convert it in this form for logarithm and we solve them. So basically the logarithmic function fx can be represented as log b of x. Now over here b is my base. Okay, now coming to the next part, location of base and exponents. We need to know what is my exponent in exponential form and in logarithmic form. Okay, so basically if I look at this expression and this expression over here, okay, if I write it more clearly, it would be b to the power y is equals to x. Okay, so over here these are my exponents. You see, in general form, in forms of logarithm, I represent it like this. It becomes a function variable. Okay, and over here you see this is to the power y. So this is my exponent. This becomes my base. The number for which the exponent is there, that becomes my base. Alright, now let's look at some of the examples, simple examples of this part. This says 2 is equals to log base 5x. What is this? This can be basically written as in this form. How do I write? Similarly for this form and this form. All of them, if you substitute using this method, you will get for 2 log base 5x, it will give you 5 square x, which will actually give me 25. Okay, so basically logarithms are exponent. This is the common term that we are going to understand. Next, it comes as 3 is equals to log base 64, which gives me b to the power 3 is equals to 64. Again, we understand that logarithm are exponents. Similarly, for log base 3 7 gives me 3 to the power y is equals to 7. Alright, so this is the basic conversion from logarithm to an exponent or vice versa. Now, look at a few examples I have just drawn. This is a table to basically how you should understand solving it. These are the logarithmic expressions. This is the question that you need to ask yourself while evaluating a particular question, and then you will get the logarithmic expression evaluated. Okay, so basically let's say if I have log base 216, 2 to what power is 16? Okay, why 2? Because 2 is my base. So if an exponent 2 is the base, to what power is 16? That is the answer that we get from a logarithm. Okay, now I get that it is 4. Why? Because 2 to the power 4 gives me 16. So that is how I get this answer will give me equals to 4. Okay, similarly for these 3 to what power is 9. I know that 3 square is 9. So log base 3, 9 gives me 2. Similarly for log base 25, 5, this gives me root under 25 is 5. So my answer is 1 by 2. Alright, now basic logarithmic properties, okay, that we need to know, which involves 1. Okay, first of all, log base and this number, if they are same, both the base and the number are same, then it becomes 1. Why? Because 1 is the exponent to which b must be raised to obtain b. You see, so basically whenever I write an expression in this form, y is equals to log bx, this is my number, this is my base, and this is my exponent. Okay, so when the base and the number they are same, this exponent will always be 1, right? Let's look at this further. If I have my base to be, the number with respect to base is 1, then it will give me a 0. Why? Because 0 is the exponent to which b must be raised to obtain 1. Anything raised to the power 0 gives me 1, right? So if this number is 1, that is, this number is 1, the exponent should always be 0, right? That is my y. So basically what we do is we need to find the exponent. So to solve the exponent part, we use this method. Now the inverse form of all these properties can be represented like this. Okay, if I have log base b to the power x is equals to x always. Why? Because the logarithm with base b of b raised to equal powers gives that power. Okay, simple evaluation. Similarly, if I have b to the power log bx is equals to x, again because it is just the rearrangement of these two forms, it is raised to the logarithm of base b of a number equals to that number. Okay, now these are the important inverse properties that you need to know while solving questions from the functions. Now, each time the substitution, you see, for x I have these two forms over here, right? So maybe sometimes we will be requiring both the forms in a different ways to solve different questions. Okay, now these are some of the general properties and common properties. We have just seen this: log base b1 is equals to 0, log base b equals to 1, log base b to the power x is equals to 0, log b to the power log bx is equals to x. Okay, similarly I have for these forms. Okay, this would be x. Alright, now let's look at some of the examples of logarithmic properties. First of all, you see, now this I can also write if I have something in the form of ba is equals to 1 when my a is equal to b. Okay, so in general form, if you need to understand, you write it in this way. So what you do is you make a chart like this. Okay, so if my n is equal to 0, that means your b will be equal to 1. So similar to this, I have when a is equal to b, my n is equal to 1. Okay, next I have, you see the example that I was just discussing, then 3 log 3 6 is equals to 6, just the property we discussed. Then again I have this, gives me. Now logarithms for natural examples of natural logarithms. Okay, you see, log, if I have some base, okay, it is not a natural log. If I write simple log 6, this becomes a natural log. Why? In that case my base is e. Okay, but when I write ln, that basically means log base of n. That is what is explained over here. Similarly, if you see it over here, so in normal form, if just log 6 is written, then you need to understand that the base is always e over here. Okay, that is the exponent. Okay, so these are the examples for natural logarithms. Now, some basic logarithm operations that you need to know. The first part is, let's say if I have log base, let it be e. In general form, you will always find e. A by b. This operationally it can be represented as log a minus log of b. They both have the same base. Similarly, if I have log a b, it can be represented as log a minus log, a plus log b. Let's say if I have some form like log x y by z, then it will follow the same operations as log x plus log y minus log z. Okay, so these are the important operations point that you need to know. Okay, in this chapter, this is all that we have in logarithm. That is why logarithm is a very small part. Okay, earlier logarithm used to be one complete chapter, but it has been reduced because not too much information is there from this chapter and the content overall is very less. It is just an application tool, okay, like fully functional tool which is required in function. That is why logarithms is restricted to only this much. Now, we need to understand the characteristic form for fx equals to log base of x. Now, for characteristic graph, okay, what we will look at in this form is, we will look at the graphs formed by our log curve. I have already explained this to you that any function if you try to put it on a graph, it will give you some curve. Now, let's look at how the logarithmic curves look like. First of all, the x-intercept is always 1, okay, and there is no y-intercept. Next part is that the y-axis is a vertical asymptote, that is x will be equal to 0. We get this from the expression part, y is equals to log bx, right? X and y represent my axis. Now, let's say if my base lies from 0 to 1, the function is always decreasing, okay, and if b is greater than 1, then the function is always increasing. Also, the graph, if you look at it, it is very smooth, it is simple curve, but it is continuous. Okay, let's look at it. For any function, that is fx is equals to log base of x, if my base lies from 0 to 1, the curve will look like this. Okay, simple curve drawing like this form. Okay, you see the curve, it goes just like this. Basic property, you remember exponential curve, how they look like. It is just in the opposite form of that. Okay, it is going towards this direction. Now, the next part is, I need to understand, for if my b is greater than 1, what will happen in that case? The graph will go like this. So basically it forms like this. Okay, the curve will be like this. So these are the two forms that you need to remember. Now, let's say I have this graph, okay, and I have given you this equation in a rectangular coordinate system. First, you need to set up a table of the coordinates for this given function. Okay, if I reverse these two for this given function, how will I get my graph? Let's look at the table. I have x for fx equals to 2 to the power x. For these, I'll have simultaneous values would be like this, right? And for x and log 2x, I have the values will interchange, right? It will give you reverse coordinates. So for the same, I have my basic graph would look like this. You see, for fx to the power x, my curve will be like this, and for fx log 2x is to like this. So what do we understand from this? And this is the dotted line, it represents y is equals to x. Now in this we understand that both the exponential and logarithmic curves are reflexive to each other. Okay, so if I know that this is my logarithmic curve, the corresponding exponential curve will go like this. Okay, they will always be proportional, that is, it will be reflexive. Now let's come to the, so that will all be in the logarithmic part. Okay, now let's look into the next part. So that is all in our part 4 section. In this part you studied logarithm, their basic definition and their basic operations. Also with the end of part 4 we come to the end of our chapter. So up till now you have studied everything is to know in functions and logarithm.